This topic sampling process. So already we discussed about the sampling process. So anyway, it is a basic operation in DSP and DEC. The sampling process is a basic operation in DSP subject as well as digital communication subject. So please try to understand it instead of thinking as a question for IA or for final exam. Okay. The topic starts from the topic a representation of periodic signals. Signals referring to equation solution of m equals to minus n to the plus infinity z of t minus m t naught ft pair f naught summation n equals to minus n to the plus infinity z of n f naught delta of f minus n f naught. The equation, I will take this as equation A because it is not a part of the sampling process. So who is that? I think please mute from your side. So this equation are taken as a because it is not a part of sampling process. It is copied from the chapter 2, which is a representation of periodic signals. From that we have copied it because it is a basic reference for the sampling process. Okay. After having this equation, after copying that equation, so next part is to make observation of that equation and you write what actually it is in its practical concept. After writing in a mathematical form, what actually it is in a practical or in a theoretical way. So that is what observing the above equation is an important conclusion. Observing above equation A. See what actually right hand side and left hand side and what the symbol basically. The symbol indicates what? FT pair. FT pairs. So FT pairs means this is going to become time domain and other side is going to become frequency domain. You know Fourier transform is used to shift from time domain to frequency domain. That's what the left hand side is in time domain and right hand side is in frequency domain. It is a one important observation. The next is what? What exactly the nature of a left hand side component and a right hand side component. So it is z of t minus m t naught is representing a periodic signal in time domain. Is representing periodic signal in time domain with period t naught. So that interpretation of the mathematical terms are very important. So that is what the left hand side of the equation A is representing a periodic signal in time domain with period t naught. Similarly, on the right hand side of this equation A, basically it is representing what? Delta of f minus n f naught, where n is from minus infinity to plus infinity, an integer. So we get a delta sequence of delta functions infinite, because n varies from minus infinity to plus infinity. Because of this, the delta functions are available in the form of infinite sequence with amplitude of each delta function g and f naught. At that value or at that instant, the value of the spectrum is going to act like a mass function of this delta function, or the weighted by the factor of this. So it is representing infinite sequence of delta functions occurring at integer multiples of the fundamental frequency f naught, which is equal to 1 by t naught. Left hand side, simply it is a periodic signal. So in time domain, it is a periodic signal, and in frequency domain, it is in the form of infinite sequence of delta functions occurring at integer multiples of fundamental frequency f naught, which is equal to 1 by t naught. So this is what exactly the observation of the equation A. The observation. That's what. So I'm going to write the observing the equation A. So this right hand side is representing what? Ft of the periodic signal. That's what I'm writing. The Ft of a periodic signal with period t naught. This is what the word periodic signal in time domain with period t naught consists of Fourier transform is the right hand side, consists of an infinite sequence of delta functions occurring at integer multiple of the fundamental frequency f naught, which is equal to 1 by 2. Okay. So this is the first important point related to equation B. So what actually it is? At left hand side it is a periodic signal. At right hand side we have its Fourier transform, which is basically consists of an infinite sequence of delta functions occurring at integer multiples of the fundamental frequency f naught. F naught is the fundamental frequency, which is equal to 1 by t naught, where t naught is the period of periodic signal on the right hand side, left hand side. So next is on the basis of this observation, on the basis of the above observation, we may state that making signal periodic in the time domain has the effect of sampling the spectrum of the signal in the frequency domain. See, we are creating a statement from what? On the basis of above observation. This observation is here. Yes, in the observation we are writing the statement what actually this equation basically. After writing the observation of the equation, then you are creating a statement. Based on that observation, we are creating the statement. What statement it is? Making signal periodic in time domain has the effect of sampling the spectrum in the frequency domain. This is going to look like a sampling process because delta of t is there at a particular instant with an amplitude of this much. Similarly, n equals to 1 f naught, 2 f naught, 3 f naught. Yes, delta of t is there, and over the height of the delta of t is equals to g n f naught. So g n f naught is what? The amplitude of the spectrum at that instant. So in this way, delta function measures the spectrum amplitude at the given instant. Is called as sampling. So based on that, we are writing a periodic in time domain. Periodic in time domain has the effect of sampling the spectrum of the given signal in frequency domain. Okay, so this is one of the important statement. This is what the statement is very important. This statement is only based on the observation of equation A. The observation is this. By referring to this observation, I can create a statement like this. Okay? So this is a second important point. Third point is there. Third point. Now I am using this statement. I am using this statement along with one of the important property called as duality property of the Fourier transform. Duality property of the Fourier transform. Duality property is basically related to an inverse operation. So it is like a Newton's third law. It is like a Newton's third law. If one side it is true, in the opposite way is also true. So based on that, so I can create another one statement by using the equations, by using the statement in the point 2. So like this. We may go on, this is one of the important conclusion, we may go on one step further by invoking duality property of the FT. Duality property of the FT is very important. By that only I can create a third statement. Duality property of the FT. We can make a statement. So we can make a statement statement in the reverse way or in the opposite way. Statement sampling in time domain. Sampling in time domain as the effect of signal spectrum periodic in frequency domain. So it is one of the important statements. So the conclusion is what? Summary. Summary I can write like this. In the time domain, if the signal is periodic, then in the frequency domain, the effect is spectrum sampling. Making signal periodic in time domain has the effect of making sampling of the spectrum in the frequency domain. So this is what we read. Making signal periodic in time domain has the effect of sampling the spectrum in frequency domain. The second statement. Third one, by using duality property. By using the duality property, I can write in opposite way. Opposite way is what? I do sampling signal in time domain. If I do sampling the given signal in time domain, then its effect is in the form of what? Spectrum periodic. It's very important table. It is based on observing the equation and creating the two important statements. So that means what? Ultimately, the summary of the observation and based on the observation, the two statements is: if you do periodic in time domain, in frequency domain it is sampling. If it is sampling in time domain, the spectrum is going to become periodic in frequency domain. Like it is in the frequency domain, time domain, there is a lot of duality property we are using. One, it is a multiplication by z 2 pi f is equal to differentiation of that signal in opposite domain. That another one of the important property of the Fourier transform based on the duality property. In one domain, if you are multiplying in frequency domain, if a signal is multiplied by z 2 pi f, in the time domain it is equivalent to differentiation of that signal with respect to time. A duality property. If the differentiation is there in the time domain, you can take it in frequency domain. It is the signal spectrum multiplied by z 2 pi f. This is another one example of duality property concept. Similar to that, if it is periodic in time domain, sampling in frequency domain, sampling in time domain, periodic in frequency domain, vice versa. So the topic sampling in time domain, making spectrum periodic in frequency domain is the topic of the module 4. The starting topic of the module 4 is what? Do the sampling in frequency domain, prove that spectrum is periodic in frequency domain. So that is what the equation 1. So equation A is very important. So in the equation A we concluded this table. Just in short, the observation of equation I can simplify in this fashion. But whenever it is required, we need to able to expand it in the appropriate interpretation form. So that's what. Now I start the sampling process. Now I start a sampling process and finally I have to prove its spectrum is periodic. So sampling process, just try to understand in general what is sampling process and what is its importance or significance. Then we will do it, its details or in a detailed way. Sampling process is usually described in time domain. Usually we do sampling in time domain. And it is a basic operation in DSP and DC, digital signal processing. The sampling process is base. Even in digital communication is also. That's what for a communication engineer, sampling process is a basic operation. Okay. So next is What actually we are doing in sampling? Through the sampling process, through the use of sampling process, an analog signal is converted into a corresponding sequence of samples. Analog signal is converted into its equivalent or corresponding sequence of samples or sample values. So try to understand what is the input of the sampling process, what is the output of the sampling process is very important. So what is the input? Analog signal. What is the output? Sequence of samples or sequence of sample values. A number, we are getting an output. And those samples are spaced uniformly in time. The samples are spaced uniformly in time. If you do sample uniformly, we do uniform sampling. Okay. After discussing about the sampling process, which is basically time domain, which is a basic operation for DSP and DC subset, and basically sampling process converts analog signal into a sequence of sample values. The next question is, at what rate I need to do sampling? At what rate I need to do sampling? If my analog signal, if it is my analog signal, if I do sampling first, here if I measure the amplitude of signal at T1. So next, at what instant I need to take T2? Is that T2 is here, here or here? So what is the next T2 position? So that is called as a sampling rate or sampling period. This gap is called as TS, sampling period, or it is equal to Fs, which is equal to 1 by Ts, sampling rate or sampling period. So what is the sampling rate I need to select as a question? Yes, sampling I can do, but at what rate, at what speed I need to do it? That's what. One of the important information is what? For the sampling process to have a practical utility, for a sampling process to have a practical utility, it is necessary to choose the sampling rate properly. It is necessary to, that's what, one of the important conditions is what? For sampling process, you know sampling process means what? Converting analog signal into a sequence of sample values or samples. So, if I am doing it, what rate I need to do it? For a that's what, for a sampling process to have practical utility, this practical utility, practical significance, it is necessary to choose sampling rate properly. This word properly, I have to select the sampling rate. Then properly means what? Properly means what? So that word properly, selection of the sampling rate itself is explained by the sampling theorem. We know sampling process, but it is not sufficient. Your sampling process must implement that sampling theorem. That sampling theorem gives you what is the sampling rate that gives a practical utility for the sampling process. Okay, so now we start with the yesterday's talk with this sampling theorem topic. Now we will start with the sampling theorem. Sampling theorem is simply gives at what rate we need to do a sampling, or the rate of sampling process it defines. So that means what I have to do sampling process first, then I have to think what exactly the rate of sampling process. Okay, so that's for that purpose we first start with sampling process, then we will think on at what rate I need to do sampling process. Okay, consider an arbitrary signal z of t of finite energy. This word finite energy means Fourier transformable. The signal must be Fourier transformable. If it is a finite energy, then it is going to become transformable, which is specified for all time. Okay. Definition of a signal g of t, which is finite in energy and specified for all time. A segment I will take because it is specified for all time. So means for every instant of time it is having its amplitude, but I am not drawing it for all the time. I will take a segment of that. That's what a segment of z of t is shown in figure 1a. So I will take this. Is what a z of t, a segment. It is not a complete segment. Z of t after taking the signal, next is what? Do the sampling. That's what. So next operation is suppose we sample z of t instantaneously at a uniform rate. At a uniform rate once every ts seconds. So then if I do this, what I get? Consequently, we get infinite sequence of samples spaced ts second apart. Okay, this is what I do sampling first. Sample z of t instantaneously. By doing this, we get samples, infinite sequence of samples spaced ts seconds apart. So that I will show you what exactly. Try to understand. Sampling is what? Sampling is the process of measuring the signal amplitude at a given instant of time. So that's what. If I take the instant of time is what? At 0. So you take it regularly. This is the 1 instant. At 0 it is. Similarly, I take regularly. The interval is common. Okay. So even you can take the last instant. Similarly, so these are the instants. each is of spaced by ts. Okay, so this width is each interval is of ts. So if I take the sample at uniform rate once every t seconds, what I get? Infinite sequence of samples. What samples? Sample means it is a value for amplitude of the signal at that instant. So at this instant, the signal, for example, if it is a 2.2, then here it is a dot with 2.2. This is what sample value. Similarly, at this instant, again it is the amplitude of that. A number or value I am getting. This point again is going to be increased. So this is what the dots I am getting as a sample values after doing the sampling of the given signal C of t. So this is what I am getting. Actually, I represent this by Z of nts. It is not Z of t. It is not Z of t. Z of t is what? A continuous. Z of nts. G of t present at 1ts, 2ts, 3ts, 4ts, where n is an integer. So this way I am writing now this as a sequence of sample values by the symbol G of nts. Lowercase g because it is in time domain only. Lowercase g, time domain, always lowercase for time domain, uppercase for frequency domain. So this is what I am getting output of the sampling process. A sequence of sample values. Sequence of sample values I am getting. Okay. The next, and this process is called as, and this sampling process is known as ideal / instantaneous sampling. Ideal means only theoretically we can implement. It's not so easy to think of practically. Okay. So then next, what exactly I am getting G of nts? Basically, is it a signal? Or what actually it is? Basically, G of nts is what? Sequence of sample values. It is simple a number. Maybe it is 2.2, 2.3, 2.4, 2.3, 2.3, 2.3, or some numbers I am getting. When I do the sampling of a given analog signal, so the output of the sampling process is a sequence of values or numbers. Therefore, I represent it is in the form of what? Sequence of values Z of nts. It is not a signal at all. It is not a signal number. A value I am getting it. But as a part of communication, I have to represent this in the form of a signal. So for that purpose, I am using delta function, because delta function is not affecting this. Delta function means what? Area under that function is equals to 1. 1 into this signal, this value means it's going to become that value itself. But that value is available as a signal. So that's what I am using a sequence of delta functions which is uniformly spaced at the rate of fs. These are the delta functions I am using. This is what? Delta of nts. Delta of t is there at t equals to 1ts, 2ts, 3ts, and so on either side. Minus 1ts, minus 2ts, and so on. Because n starts from minus infinity to plus infinity. So I take a Dirac delta function, a sequence of Dirac delta function. infinite sequence of direct delta function. Next, I will multiply these two to convert this value into a signal. To convert this value into a signal, I multiply this delta function, which is equals to 1. 1 into 2.2 is equals to what? It is a 2.2 only, but it is available in the form of a delta function. It is not a number now. Once I multiply this into this, it is available in the form of a delta function with an amplitude of a sample value 2.2. So now it is available in the form of a signal, direct delta function. Now it is only a number or a value. But in my communication system, that number is not going to work. So it should be present in the form of what? A signal or a function. That's what to convert that value into a function or a signal. I am using the sequence of direct delta function. You know that the area under this function is equals to 1 into this value itself, but it's going to be available in the form of a delta function. So what output I am getting here? So I write this as z delta of t. The product of these two components I am writing as z delta of t. What z delta of t will get you? So at this instant it is 1 into the sample value. Assuming the sample value is 2.2. 1 into 2.2 is what? 2.2 with this delta function. Now the delta function is there with an amplitude of 2.2. Similarly, second one is having 2.3 or 2.4. It's greater than this. So it may be again a delta function with more amplitude. Third one, this is a bit greater. Fourth should be less small. The fifth one, this point again it is positive, and for this it is going to become negative. The signal I am going to get like this. See what actually it is. I will take this as figure 1a, and it is B, C, and D. A is. See, A is my analog signal. A is my continuous analog signal. B is after doing sampling process. So what I am getting exactly after doing sampling process? I will get the sample values. That value is a number. So this is what the dots are representing the value or number or sample value at that given instant. So once it is present in the form of a sample value, I convert that into a signal without affecting the sample values. So for that purpose, I am using a sequence of direct delta function at a uniform intervals, same as my sample values. Then I multiply figure B with figure C. The product of these two is represented by Z delta of t. Okay, so now you try to write this operation which is graphically shown in the figure A, B, C, D, particularly by using, because A is my input signal, B is a sample value, D, C is going to convert it into a sample values into a signal. I am using delta function. When I multiply these two, I get Z delta of t. So by observing the A, B, C, and D, we can write the equation or mathematical form for figure D. For the figure D, the mathematical form, what the Z delta of t actually. So try to think on how to write. You know figure C, figure D, figure B, and you know basic operation between the B and C. Based on that, you write the equation for Z delta of t. That's the figure D. What Z delta of t is equals to? Anybody? So for explaining the operation, Z delta of t is equals to, how you are going to represent this Z delta of t? Actually, it is the product of figure B and C. It is the product of these two components. Figure D is equals to figure B into figure C. So what the mathematical way to express Z delta of t in terms of figure B and figure C? So it is equals to what? Summation of n equals to minus infinity to plus infinity z of NTS, that is figure B, z of NTS into delta of T minus NTS. So equation number 1. See, this is what the equation number 1. Just one first equation we obtained for the fourth module. But getting this equation by referring to the theoretical operation and representing it in a diagrammatical form and representing finally in a mathematical form is also very important. So don't try to back it. Try to think on what we are doing, and the same mechanism must be represented in a mathematical form. So it is what? A product of figure B and figure C. The combination, yes, it is there. Delta function is there at minus infinity to plus infinity because your n is varying from minus infinity to plus infinity. Therefore, a summation of the product of figure B and figure C, the corresponding components. Delta function at this point, sample value of that get multiplied. Therefore, NTS, NTS, 1TS, 1TS, Z of t at 1TS into delta of t at 1TS get multiplied. Similarly to 3, even you can substitute n equals 2, but in all the way it is going to become parallel. Minus 2, 3TS, minus 2, minus 1, 0, 1, 2, 3, TS, 1TS, 2TS, 3TS, 4TS. Similarly on left hand side, minus 1, minus 2, minus 3, minus 4. So the same instant we have a delta functions, the corresponding elements will get multiplied, and summation of that gives you from minus infinity to plus infinity is z delta of t. So the equation number 1. Okay, so we refer z delta of t as ideal sampled function. We refer z delta of t. The name of z delta of t is called as what? Ideal sample signal. This is very important. Repeatedly I am using ideal sample signal, z delta of t. Why it is called as ideal? Because of this delta of t. Because delta of t is an ideal function. It's not possible to generate that delta of t by any instrument practically. Because you know delta of t is there at only at t equal to 0. You know the definition of delta of t. It is there at t equal to 0 and it is having area under that curve must be 1. So I think it's not so easy to realize that things mathematically first of all, then practically it is not at all. Therefore, if it is as it is involved with the delta function, I refer that sampling process as the ideal sampling process. A line, the signal is a line having width 0, height infinity, which is not possible to generate that signal by using any practical generator. Okay, so that is how. The next is what? This delta of t is representing what? A delta function at t equals to NTS, maybe 1TS, 2TS, 3TS, and so on. Okay. So from the definition of delta function, we know that idealized delta function has a unit area. So therefore, multiplying factor z of NTS, because it is equals to 1 always. So it is equals to 1. As 1 into this, finally it is going to this value itself. That's what the multiplying factor z of NTS in the above equation 1 viewed as mass assigned to the delta function. Because see, what is the value of delta function here? 1. What is here? What is the value of delta function here? It is a sample value. For example, if the sample value is 2.4, the delta function here is a 2.4. If the sample value is 2.5, the delta function is going to become 2.5. So means what? G of NTS decides what exactly the weight or amplitude or mass of the each delta functions, because basically delta function is equal to 1. So 1 into that value itself is the value. It is not having any effect. Okay, because of that, G of NTS viewed as mass assigned to the delta function. It is a mass assigned to the delta function. So means this height is directly proportional to the Z of NTS. There is no role of delta of T. Okay. So this is what now we obtained equation 1 and equation A. Two equations we are having now. So by using these two equations, next we will move to find the Fourier transform of the equation 1 by using A and by using general Fourier series, Fourier transform definition. By using two methods, it is possible to find the Fourier transform of the equation 1. Because I have to prove, yes, I am doing sampling in time domain, then I have to think of what the frequency domain component. Ultimately, it should be what? Periodic. I do sampling in time domain, then I have to prove its Fourier transform in the frequency domain. The spectrum is going to become periodic. So in the afternoon class 3 to 4, so we will start with the discussion of equation 1 in comparison with the equation 2, generating the equation, sorry, in comparison with the equation 1, generating equation 2, which is giving you a Fourier transform or FT pair for Z delta of T. It is a one method. Again, by using directly Fourier transform procedure, it is possible to find the FT of this equation. So by that, we will get the equation 3. By using comparison of equation 1 with A, we generate one FT pair for Z delta of T. And by using general procedure of Fourier transform for the equation 1, we generate Fourier transform of the equation 1. So in this way, we are generating two types of FTs of the equation 1 available in the form of equation 2 and 3. That is going to cover in the afternoon class 3 to 4. That equation 3 and 4 are very important for the next case, in which case we are going to take a particular periodic strictly band limited signal. By taking that strictly band limited signal, we are finally proving that what is the sampling rate we need to follow. Okay.